Hello and welcome to lesson 6 of chapter 3, part 3, which is derivatives of inverse trig functions. So before we get to doing the actual derivatives, a couple reminders about trig and about inverse functions. So first, in order for a relation to be a function, remember that it would need to pass a vertical line test, or for every input, there's only one output. In order for an inverse to be a function, the original function would have needed to be 1-to-one. So if I draw myself a sine curve here, it's not going to be very pretty, but there we go. Okay. If I draw myself a sine curve, so first remember this is at pi, this is at 2 pi, this is at pi over 2, 3 pi over 2, negative 1, 1, be negative 2 pi, negative pi, pi 2. Okay, so if I have this lovely, beautiful sine curve, if I were to draw an inverse of this, the problem is that my inverse is going to look like this, right? And that's not a function. And we know from earlier this chapter, just by looking at sine of x, this is not the inverse of this would not be a function because this is not 1-to-one. So this is sine x. And we can see that this is not 1-to-one. What that means is that the inverse of this would also not be a function. So if a function is 1-to-one, the inverse will also be a function. This is not 1-to-one, the inverse would not be a function. We can't do a derivative of the inverse trig function if it's not a function. So the first thing that we need to talk about is how can I restrict the domain of this so that it is 1-to-one and therefore is a function? There's a couple ways I could do that. If I, for example, start my domain here and start moving over to the right, as soon as I hit this point here and go back down this curve, my y values start repeating and I'm no longer 1-to-one. So I would have to stop at this pi over 2 value here and not keep going. So I could travel from 0 up to pi over 2 before I start heading down that curve and start repeating my y values. The other option is I can head in the other direction off to the left. And again, once I get down to this negative 1 y value, as soon as I round that corner and head back up the curve, I'm getting multiple y values that are the same as each other. So I can't do that. I'd have to stop here. So what this means is if I were to redraw this from negative 1 up to 1, I'd be going from negative pi over 2 to pi over 2 and would be a 1-to-one function. As soon as I continue past this in this direction or past this in this direction, I would be no longer 1-to-one as I would have y values that repeat themselves. So the box below just states exactly that. If we restrict the domain from negative pi over 2 to pi over 2, then we do have a 1-to-one function. Okay? So inverse sine function, just a reminder, is if you have sine with a little negative 1 of x, this is the same as saying sine of y equals x. So really here, remember that this y here, is an angle. Okay, and x is a ratio of triangle sides. For sine specifically, that's opposite over hypotenuse. So the x and the y in these two equations here are the same x and y as each other. It's just written in a different form. Now that we have restricted the domain, this would be our new domain, and this would mean that the inverse sine is also a function. There is another notation you're going to see here, which is arc sine. Okay? And the reason this is written is because people get confused with the little -1. They think this means reciprocal function because they think this is an exponent. It's not an exponent, it's indicating inverse, but we do have this other notation. So the inverse sine is also written as arc sine x. Similarly, inverse tangent would be arc tan, inverse cosine would be arc cosine. So you have this little new notation just in case you run into it here that you might see. Okay. So for example, if I want to say find secant of inverse sine of 2/5. Okay. So remember, if you're doing the inverse sine of a number, this is going to equal an angle. Okay. So I'm going to let this angle be theta. Then what I'm actually trying to find is I'm trying to find secant theta. Okay. Or 1/cosine theta. Now, the problem is we don't know theta. We need to find theta. So if I use this information about sine, I know that sine, if I have some angle, is opposite over hypotenuse. And I know that sine of this angle would equal 2/5. Or inverse sine of the ratio will equal that angle. Now, I know that this angle that I just put in here is the same as the angle in the information on the left. So I know that secant of theta is 1/cosine theta. Well, I can find cosine theta here. It's adjacent over hypotenuse. And I can find the adjacent side. I'm going to say the adjacent side is x. Adjacent, x squared would be 5 squared minus 2 squared, or 25 minus 4, or 21, or x would be root 21. This means that cosine theta is equal to root 21/5. Well, if cosine theta is root 21/5, 1/cosine theta is 5/root 2. So really the key here, looking at a question like this usually freaks people out because they're like, oh my goodness, inverse sine, what does this mean? Well, we know inverse sine of a ratio is always equal to an angle. So really all we're doing is we're finding secant of that same angle. So I would draw yourself a picture. You know that this means that you have an opposite side of 2 and an adjacent or a hypotenuse of 5. You've got an angle in that triangle somewhere that these sides are referring to. And then you know that secant of that same angle is really what you're trying to find. Also, remember that if you have the inverse of a function, that was equal to x, and that's asking, is that true for sine? And the answer is no, because this is only a function for a certain domain. So it's only true if the domain is restricted. So from when we did our inverse functions in lesson 2, we saw that this worked if the inverse was a function. So this statement is only true if inverse sine is a function, which is only true if we restrict our domain. So unless it says somewhere our domain is restricted, the answer is no, it's not a function. And it's not true. Okay. All right, now we're going to try this one. Again, I would draw myself a picture. So first the question is, well, what does this equal? This equals a ratio of sides, right? We have some sine theta equals some other thing, right? And we plug that other thing back into sine. So if I draw myself a picture, sine of 2 pi over 3 be over here. I know that this is a special triangle with a reference angle, pi over 3. So my sides of my triangle are 1, 2, and root 3. A little technical difficulties here today. Now I know that this one is also a negative 1 because we're on the negative x-axis. So this means that sine of 2 pi over 3 is equal to root 3 over 2. Now I'm asked to find sine inverse of this amount. So sine inverse sine of 2 pi over 3 is the same as finding sine inverse of root 3 over 2. And inverse sine of root 3 over 2 is going to equal an angle. So the other way of saying this is sine theta equals root 3 over 2. And again, if I think about a triangle and I've got an angle in that corner, my opposite therefore is root 3. My hypotenuse is 2. My other side would be 1. And this means that theta would be pi over 3. Okay. So in other words, theta equals pi over 3. So the reason this doesn't equal 2 pi over 3 is because it doesn't, that 2 pi over 3, we know that usually when we solve a question like this, we would get two sets of answers, right? We would have one answer, usually we'd have one answer in quadrant 1 and one answer in quadrant 2. But because we have this inverse bit here, we know that in order for this to work, this inverse has to be a function. Which means that x must be between negative pi over 2 and pi over 2. And that's why I'm only including this part here. I'm not going to include this answer. Does not in my domain for my inverse to be a function. So I can only use this inverse function here of sine of 2 pi over 3 if it's an actual function, which only happens as we saw on the front page for this domain, negative pi over 2 to pi over 2. This is why I'm not going to include both sets of answers that I would usually include. All right, now this domain issue comes up with the other trig functions as well. So we've got inverse cosine, inverse tangent, and inverse tangent. And here you can see what the restrictions on our domain are for those angles in order for these inverses to be functions. Now, secant x and cosecant x, you can see, are not here, and that's because they are not universally agreed upon. Usually, the questions that you will see are mostly inverse cosine, inverse tangent, and inverse sine. Even cotangent come up much. Okay. So if I wanted to simplify tangent of cosine inverse of x, again, we know that this is going to equal some angle. If I say it equals y, then I can rearrange this to be cosine y equals x, right? If I do that, that means that y is my little angle in the corner. I know that cosine is adjacent over hypotenuse. So in this case, this means my adjacent is x. My hypotenuse must be 1. Okay. This means I'm finding tangent of y, since I said that cosine inverse was equal to y. So if I want to find tangent of y, I know this is opposite over adjacent. So I probably need to find an opposite side value here. So my opposite squared would be 1 minus x squared, which means my opposite side is going to equal the square root of 1 minus x squared. So my tangent of inverse cosine or tangent of y would equal opposite 1 minus x squared square rooted over adjacent, which is x, okay? Or I didn't have a y in my question. Tangent of inverse cosine is equal to 1 minus x squared square rooted over x. So really when you're doing, if you hopefully have noticed in all these questions, the first thing I'm doing is drawing myself a triangle, maybe rearranging whatever the inverse is to be written in the way we're used to seeing it. So we know that if we're taking inverse of something, when we do the inverse of something, that something must be a ratio. And so the answer that pops out when we do an inverse of something will always be an angle. So if I'm doing tangent of an inverse, I'm doing tangent of an angle. And the question is, can I come up with what that angle is, basically, so that I can find my tangent of that. So we're going to use some of this information to try and help us come up with how to find the derivatives of these inverses. Okay. So these first couple questions were mostly just trying to get a little bit comfortable with inverses when you don't actually have numbers and how those relate to a picture. Okay. So we're going to now extend this to actually finding the derivatives. Most of your professors in university will not give you these derivatives. So if you scroll to the next page, you'll see I have this huge chart that tells us all the derivatives. And we're going to do an example down here, number 5, where chain rule applies. So you don't have an x inside, you have a root x. So this derivative that's in the chart doesn't apply directly because it's not an x, it's a root x. So we will take a look at how that works. But the first question, we're going to actually show you how to come up with these. Because when you do this course in university, this chart will likely, unless you have the most generous prof to ever walk the earth, this chart will not be given to you. So that either means you're memorizing this entire chart or you're able to find these on your own. Okay. So I want to find the derivative of an inverse, but I don't know how to do that yet. So what I'm going to do is I'm going to rewrite it into something I do know how to find the derivative of. I know how to find the derivative of sine, not inverse sine, sine. So I'm going to rearrange this so that it's written as sine of something instead of inverse sine. And we know from our information about inverses that sine y, therefore, would equal x. So in this case, the y is the angle and the x is the ratio. Anytime you do an inverse trig function, they input a ratio and they output an angle. So that means that y is an angle and x is a ratio. Okay, so if I rearrange this, we know that if we do a regular sine function, we're inputting an angle and outputting a ratio. So I'm going to rearrange this, and now I can do the derivative of this. Okay. So the derivative of the left, the derivative of a sine, is cosine. So if I want to do the derivative, I would have to take the derivative of both sides. The derivative on the left is cosine y. And then I also need to be able to do the derivative of the inside. The derivative of the inside, the derivative of y, which would be dy dx. And on the right, the derivative is 1. Now I'm trying to find the derivative, so I want dy dx by itself. So I get 1 over cosine y. Now the problem is I shouldn't have y's in here because I'm finding the derivative of inverse sine. I should have an x. But if I go back to this idea of drawing my triangle, I know that for sine y equals x, y was my angle and x was my ratio. We know that if sine y equals x, this is opposite over hypotenuse. That means my opposite must be an x, my hypotenuse must be a 1. Now, the problem is cosine y is adjacent over hypotenuse. I don't have my adjacent here. I need to find it. So if I want to find my adjacent here, I would have my adjacent squared is equal to 1 minus x squared, or my adjacent is the square root of 1 minus x squared. So this means that cosine y is equal to root 1 minus x squared over 1. My hypotenuse was 1. This helps me over here. This means that 1 over cosine y is equal to 1 over root 1 minus x squared. And therefore, my derivative of inverse sine is equal to 1 over root 1 minus x squared. So if you don't draw a picture and kind of figure out that adjacent side, you get stuck right here. This is not the way you would write your answer. You would want to write it like this, okay? Or like this, which is in our chart below, right here. You can find all the other inverse trig function derivatives in the same way. Rearrange, label a triangle, find the derivatives using your regular trig functions, and then make sure that you resubstitute back in for y at the end. Okay? So we're going to try a question where we're actually going to find a derivative. Okay? We're going to do the derivative of the inverse tangent. So we are going to need to use this one right here. Now, chain rule applies for all these questions. So whatever you see here, whether that's just an x, whether this is an entire absolutely disgusting function, this goes here. So for us, what we really have is we have inverse tan of some function. That's what we have, which means y prime is going to be 1 over 1 plus that entire function squared, because instead of an x, I have an f of x. So you'll see that this goes in there. Well, this is going to go in there, right? Whatever's inside the inverse tan is what's going on the bottom to be squared. And then chain rule applies, so you would need to times it by f prime of x, okay? This will work for all the other inverse trig functions as well. I plug some function here, that function goes here, and I would need to multiply by f prime, okay? Now, what this means for us is this means for us y prime is going to be 1 over 1 plus root x squared, because the stuff inside my tangent is root x. And I need to multiply by the derivative of the inside, or the derivative of root x. And we know the derivative of root x is 1 over 2x to the negative 1 over 2. Or we can fix this up. This becomes 1 over 1 plus x. The root x and the squared cancel out, times 1 over 2 root x. Or you can rewrite this as 1 over 2 root x times 1 plus x. You could rationalize if you wanted to and make this root x over 2x 1 plus x. You can expand the bottom if you want. So there's a couple different ways you could write the answer, but most of you will probably just leave it like this. Just be careful that this entire thing is multiplying with this entire thing, which means that this bottom bit, the 1 plus x, needs to all be multiplied by the 2 root x. Be careful with that, okay? Chain rule applies.